So this will be there, but mostly like manipulating different underground materials and device perspective. So from the last talk, wonderfully explained 2D and 0D hybrid. So I'm talking about this word mix, 1D and 2D. So the heterostructure will be formed like from a 1D material and a 2D material. Okay. Okay. So the current status of the microprocessors which we use in our devices, usually the components are roughly like this. So they have transistors, switching elements, interconnects, gate dielectrics, and there is power management. So usually for these transistors we use silicon or 3-5 semiconductors. Interconnects we use metal, copper is the best, and gate dielectrics for hafnium oxide and power management for gallium nitride. And as you can see, the most important part of making any engineer to make a good transistor is high mobility channels for fastest switching and low power operations. And for interconnects, it should be reduced resistivity and improved electromigration resistance and faster signal transmission. Of course, for gate dielectric, that's why from silicon oxide we have moved to hafnium oxide, high K material to reduce gate leakage. And power management, higher breakdown voltage and energy efficiency in power delivery circuits. So the only thing which is yellow here is 2D materials, which in our papers we always propose, but it's not yet implemented in the current microprocessors. Of course, there are a lot of papers with it. Okay, so are everything okay with microprocessors and hetero elements? This is the first question. So there are fabrication challenges, even though it's mostly perfect, but there are challenges. So fabrication challenges, so as you can see, there could be defect densities, scaling and etching complexity, so selectivity ratios. There are different steps in fabricating microprocessors, and thermal management. So 30% of the defect rates is from materials. Electrical performance, so mobility can get reduced with time. And electromigrations, which I was talking about with interconnects, so 30% reduction in interconnect lifetimes, and scaling lifetimes below 1 nanometer, and material availability and costs, and environmental and sustainability concerns. And for that, we have published 100,000 papers maybe in last 20 years with 2D to say that can 2D replace current microprocessors. Okay, so of course 2017 there is one paper where 1D implementation of microprocessors in 2-dimensional semiconductors have been proposed. This is the complex architecture of the microprocessor. Of course it's complex, but the only limitation, major limitation of the circuit is overall yield of only a few % of fully functional devices. We create a lot of devices, only few works. And but it doesn't stop us for hoping 2D could be our future. So with time, there are predictions that 2D CMOS will have some sort of photonic integrated circuits, neuromorphic computing, and quantum technologies. So as you can see here, 2D is, they start quite fast, and now in the business of microprocessors, it is, the slope is not that high. But again, there are different applications where people can work on, and that could be integrated in microprocessors. Of course, in 2D family, you can get P-type semiconductors, N-type semiconductors, and you can manipulate to get ambipolar or anti-ambipolar characteristics, which could be interesting for the integration in microprocessor. And people have started working on graphene and 2-dimensional with different sensing techniques. So let's see. So the problem statement for us is from the starting of the growth to fabrication to characterization, can we create or can we propose a 1D 2D random or retro structure for making these sort of operations? What usually different hetero elements in a microprocessor does. So it's like unification. One simple solution for different circuit operations like switching, transistors, like that. So we will start with growth. So we have some sort of we have made a recipe to create a all CVD type of growth technique to make 1D, 2D van der Waals retrostructure. So this is not exfoliation which we will be following, it's all growth. Okay, so starting from growth, then we will try to see whether we can realize diode from these retrostructures. So diode means whenever we see diodes in our practical labs, it's like PN junctions, right? So can we create PN junction diodes with one-dimensional and two-dimensional materials? And can we create CMOS out of it? So this will be like a P-type and N-type. Let's say this is P-type and this is N-type. Can we create something like P and N and make an inverter with this? So the target is quite simple. One is like first standardize the growth to make 1D, 2D retrostructure, whether we can realize it. Second, can we create an analog electronic component, which is diode, which comes first in our mind, which is diode, and then CMOS, which is more of digital logic circuit operations. So it's mostly like PMOS and NMOS together. Of course, the last statement should be nothing can beat the present. So I'm not proposing anything which can present the silicon microelectronics or nanoelectronics. It's just a proposal which from our lab we are trying to fabricate and characterize. Okay, so I will finish with an interconnect where I was talking about copper interconnects. So let's see if we can provide another interconnect which can carry much larger current. Okay, so the team is like this. So I was blessed with two integrated MS students, Vikas, which is present here. Vikas and Vipul, they have sort of worked for this project. And for the fabrication of device, Moinak, he has worked on e-beam lithography. So Vikas has worked on growth and digital electronics part, which is CMOS. And Vipul has worked on growth and analog, which is more of diode. Okay, so for analog electronics, this picture is very common to us. Even when class 12 student can keep this picture. This is the PN junction diode, and we have all used in our practical lab. And if you see the geometry of it's all in millimeters, right? So this is all in millimeters, and the physics is quite simple. There is P-type and N-type, and you have sort of a depletion region, and depletion region forms with this different flows of majority and minority carriers. Now the point is, if we apply voltage, then of course there is a build-up voltage in the depletion region, and you have if you apply measure current. So this is the x-axis if you get source drain voltage. So just voltage between this, and you are measuring current. So as you can see, there is a cutting voltage. Usually we can remember this number 0.7. So these are very basic semiconductor physics which we are discussing now. Okay, so of course the scale is very important. Usually for a PN junction, the scale here is milliampere, and the scale here is picoampere, and that gives us the liberty to use a diode as a protection circuit in a microprocessor. Okay, so another important part is the charge density. It's like step function depending on the depletion region boundary, and electric field and the potential, which is like minus dB derivative. So all these are very elementary semiconductor physics. Usually the calculation goes like this way. We start from a Poisson's equation, then we have, depending on the dimensionality of the system, we have 2D and 1D density of states. From that we can calculate depletion region and built-in potential, which is more of something like acceptor and donor density, and then numerical simulations we can do numerical simulations depending on the system for built-in the band bending, 1D, 2D material correlations and non-uniform doping properties. Okay, So when we say we want to replace it with a one-dimensional material, the first thing which comes to our mind as 1D is carbon nanotube. This is the most celebrated 1D material which we can think of. So it's not that we have started working on these systems. Of course, people have started little earlier working on CNT MOS2. They have a different perspective of the work. So here, as you can see, there is the architecture is like something like this. This is carbon nanotube, and then there is MOS2 on top of it, and you can measure the current between this and this. So conventionally, we used to measure something like a current between carbon nanotube and carbon nanotube in these two contacts, but here the measurement is like this. So there will be some current flowing through here in this channel, right? So people have worked on it, and the heterostructure can appear as an NN junction, PN diode. They have done a lot of calculations to prove that there could be band bending tunneling. So here, as you can see, it could be before contact, and then there is a band bending between carbon nanotube and MOS2. And depending on the transfer characteristics and source rate behavior, they have modeled the system. Of course, there are challenges in the system where the power is the main thing and the energy efficiency of the tunnel bed. Okay. So how does it look like actually? So the system looks like this way. So this is the CVD MOS2. This is CVD MOS2, and this is the carbon nanotube. So this is single wall carbon nanotube and CVD MOS2, and you can measure. It's a 3-terminal device, as I was explaining. So you can put electrodes on carbon nanotube. You can put electrodes on MOS2, and then apply gate voltage, which is in this paper. Which, it's like backgate, and you can measure the drain current as a function of gate source. So this is the typical transfer characteristics people used to measure for a transistor. And then depending on again this different region of the transfer characteristics or current voltage, you can model it with thermodynamic or tunneling characters or thermodynamic characters in different positive or negative voltages. Okay, so of course this is one aspect, and then people try to work on solution process systems where you can create these heterojunctions with single wall carbon nanotube and zinc oxide derivatives. Sorry. And they have found anti-ambipolar characteristics. So ambipolar means you have a p-type and you have an n-type, and then ambipolarity means you have hole and electrons in the system. And anti-ambipolarity is the reverse of it, so you can create something like this. So usually it is like this, ambipolar. Now they are getting something like anti-ambipolarity in the system. So that can be important, as they say, that the von Neumann bottleneck, where what is the existing memory and processor system in the computer by enabling dynamic reshaping of circuit connectivity. Okay. So, to introduce our system, the most recent work I could find is this 2-dimensional tellurine, where people could chemically find a solution process where drain voltage, and then you could see this tellurine it's flat to the part, and you can sort of from this solution you can create these flakes, drop dust on the silicon oxide, and create this FET to find the transfer characteristics like backgate and gate current. Again, solution process systems have its own demerits because solution process is sensitive to the conditions such as precursor, solvent type, and temperature. So we would like to find a way where we will make one recipe and it will give us all results together. So there is no such liquid or solution grown processes. So it will be all like CVD grown. Okay, so to find the P and the N together, you can really guess that the system, if I want to choose N from the van der Waals family, MOS2 is the best choice. So 2D van der Waals N type, MOS2 is the best choice. So how can I find a P type? Now P type, finding a P type semiconductor is not so easy. From a very basic calculation, as you can see here, from the conduction band minima and valence band maxima and the metal's work function, you could find that getting a P-type semiconductor, it's very difficult. Depending on the, of course, it depends on the contacts which you are using, contact electrodes which you are using. So we started with searching for P-type prediction of 1D van der Waals. I would, in this talk, I would mention two which we have found. So from these predictions by Ivan Gireid, I think he has influenced our work heavily. So his predictions we have used this one thing, PDBR2 and the tellurine, which we have used for our applications in our work. Okay, so if we take a very simple textbook problem, that MOS2 is a monolayer, true 2D monolayer, and a tellurine is a one-dimensional chain. Now, can we, from a very basic understanding, can we calculate depletion region in MOS2 and depletion rate in tellurine, and the total depletion rate with and the built-in potential which is created in the depletion region for let's say this structure. So this structure where there is a 2D flat zone and there is one region. So of course MOS2 is flat, so it's very easy to calculate the depletion width from the 2D depletion region depletion region expression, and this 1D is like a cylinder, so you can get the cylinder in a radial way. So this is the depletion region expression for 2D 1D tellurine and 2D MOS2, and you can calculate from the numbers, and it's of the order of 6 nanometers. From a very basic calculation without doing anything from the materials perspective. So okay, so and the built-in potential is 1.1 volt, and it's extremely localized nature of this depletion region, because you can understand this is a well and then there is a 2D material. And 1D systems, I can choose anything as I was telling you, and people have worked on this. We are working on different one-dimensional systems, but for the moment, which I want to tell, it's nothing to do with the physics which is given here. But the point is, 1D system, for the moment, there are very little information about the semiconductor type of this system. So there are a lot of areas where people can work on. Okay, let me start with our results. So this is like a sequential growth which we propose here. So this is CVD growth system where we are sort of growing like step by step. So as you can see here, so this is sort of a MOS2 growth, and then tellurine growth on top of it. So tellurine is more of a PVD, physical vapor deposition, because you are starting with tellurine powder, tellurium powder, and for MOS2 it's like some reactions are going on. So it's like MOS2 first, and then on top of it is tellurine. So how the heterostructure look like? So this is one of the examples. I will show you a broader picture. So this is the MOS2 and this is the tellurine. Okay. So Raman spectra and other things, they concluded that the heterostructure formation is quite good, and the PL is okay with the MOS2. And you can see these from the Kelvin probe. You can see this the work functions across different areas, where how the work functions changes in MOS2. This region is the tellurium. So how the work functions changes here and again here. So we can really find from the work function analysis how the band bending could look like. Okay, so after the growth, usually we do fabrication of the devices. As you can see, this is the device where all the circuits are made on a MOS like this way, and this is the where all the devices are like this. So ACM picture is like this. So this is the where, and these are the devices. So if you apply a voltage here, so there will be current through this this tellurium and MOS2 frequency. And the simple density of states calculation gives us an idea about how they are hybridized. So usually valence band of tellurium 5P and MO4D is hybridized, and for the basic contribution is coming from the tellurium and MO. Okay, so from the KPFM we can see that the band bending looks like it's like tellurium is giving charge, so it's sort of a tellurium is the charge transfer is happening from tellurium to MOS2. So the good point about this heterostructure is, as you can see, this is the red region is the tellurium. So you can do all sorts of analysis here, which is hybrid, and then here, which is another isolated region. Okay, so what about the characteristics of the hybrid? Means the with the hybrid. So now the current will be something like here on tellurium and MOS2. Okay. So this is the typical diode characteristics which I was talking about. So as you can see in the negative bias, it's completely blocked, and forward bias there is dependence, and you can sort of see the temperature dependence, which is not important for this talk. So the point is, this is this architecture of measurement. So as you go forward bias, as you can see here there is a change. So that's most important, because for this diode you can tune the threshold voltage, which is not so common in our course, right? I mean, in our technical lab, what diode we are using, usually for silicon diode 0.7, if someone asks you to change the threshold voltage, it's very difficult to change threshold voltage of a bulk diode. Okay, so the takeaway message from this is you can change the threshold voltage, and the mobility of different transistors can be found like this. And the most important part is the calculated depletion with this 7 nanometer. And huge electric field has been built, which is of the order of 10 to the power 7. So that we have checked with from the help Dr. Kopil Devduri, University of Cambridge. He did specially resolved band bending spectra, where you can see that the valence band is not that much affected, but there is a band bending here in this here. So this is sort of, just mind it here, this is the x-axis, so this is the space coordinate. So the band is like a space coordinate, how is it changing. So now if we want to see the transmission and resulting charge density and voltage build-up or electric field, it comes like this way. So as you can see, this is the change in there. So here the charge is like this, where the interface is formed, and this is typical electric field, and this is the potential characteristics, voltage. So that is quite reminiscent of what we see in our textbook in diode. Okay, I would like to finish this talk by the non-hybrid region, because when you grow systems with CVD, there could be regions where the wear is not on top of the MOS2. So you miss the MOS2, right? So PN is not formed. But that is also useful, because that there you create a circuit where P and N can be combined to create PMOS and NMOS, so CMOS. Since I'm running out of time, so we have used ionic liquid to enhance the gate dependence, because our gate is silicon oxide. I do not have hafnium oxide with me. So if you have hafnium oxide, the same experiment can be done with the system. So let's say I have an effective gate, which is ionic liquid for the moment, And I can create these sort of CMOS circuits where PMOS is this is N and this is P. So this is like what you have studied in your switch figure in your digital electronics course. So from the PMOS NMOS you could create these sort of circuits where N and P can be combined. So you can find a region where CMOS would operate. So this is the basic architecture of this. Let's say this is the broad area image of the hybrid circuits, where you could find only where and the MOS2 circuits. So there you could find this is the complete architecture of CMOS. We have followed exactly like this way, and we have found the basic logic operations with CMOS, where you can find the gain from the view of being and different logic operations. I'm not going into the details of the universality of the universal gates, the simple AND or NOT gates where you can realize with these systems. Since I'm running out of time, I'm not going into the interconnects, but we have found an interconnect which is good, but yeah. Okay, let me conclude this presentation by saying that the 1T2B van der Waals hybrid could be a solution for making mixed dimensional diode where you can control the threshold voltage indicating and the diffusion region of the order of 10 nanometer with huge electric field can be used for different applications. So that we have find out in our systems, building and MOS2.